All right, so, okay, forgot to turn on the mic. All right, so I am checking the volume in Discord and also in OBS. So I think I'm not clipping today because I dial back the gain of the mic. So hopefully, the audio will sound a little bit better today. All right, so we got about 2.5 minutes before the class starts. I can answer questions if there are any prior to the class. Okay. And okay, so Tom is typing, so we'll check out what he has to say. Okay. Well, there are usually two things that you need to do. There's usually at least one active lab and also the role-taking activity, which I hope people would do pretty much as soon as I disclose the word for the role-taking activity. So yeah, those are the usual things that we do. Reading ahead of the class is going to be helpful too. So at least catch up, in terms of the reading of where I stop. And reading ahead by about one module would be very helpful as well. All right. So we got about 1.5 minutes. All right. So I sent out a few, email to just a few individuals about the CISP310 prerequisite. I'm really just talking about like 2 or 3 people in the entire class. So most people are fine in terms of passing the prerequisite check. But for those people who received the email from me, asking for prerequisite verification, so you probably need to get that taken care of soon. Okay. All right. All right, so we got about 40 seconds, and what I'll do is go back to the topic that we were talking about last time. All right. And I believe it is almost time. We got about 10 seconds to go. The YouTube site should be streaming already. Yep, punctuality it's something that is not expected. I'm not sure how many of you have done an MBTI or Myers-Briggs type indicator personality test. So my type is INTP, which is not really known for being punctual or on time. So this is one of the odd things that I do, when I teach classes. I tend to be on time. All right, so it is time. The first thing we are going to do is to go back to the note or the module that we talked about last time. And we are really down to the last one, which is number 4. So what number 4 is saying is, what we're really doing is we don't really need to look at physical states anymore, after this module, because what we do is we look at 0 as a voltage that is below a certain threshold, and we look at 1 as a voltage that is beyond or above a certain threshold. So we are not really kind of doing, oh, okay, that's kind of cool. So we are now stepping away from physical quantities as well as physical devices and starting to get more into logical operations. Okay. But before we get to logical operations, let's kind of just recap what a computer or what transistors can do. So when you look at section 3.4, section 3.4 is basically saying, with a NAND gate, we can implement a normal negation, we can implement a normal conjunction, and we can also implement a normal disjunction. So all the logical operations or Boolean operators that you have learned in C and C++ can indeed be done using a NAND gate. Okay, so that's great. Okay, so now we know we can use transistors. Okay, now you can say that, but there's a whole bunch of transistors. Look at this thing here. There are two NAND gates. Okay, this is one NAND gate, and this is one NAND gate, and this is one NAND gate. There are three NAND gates. Okay, to perform a simple OR operation. Well, that may be the case, and it may not even be optimal, but the whole point is it is possible. Okay, we can indeed use transistors to implement negation, conjunction, and disjunction. So this is great, but computers are not, they do not just perform Boolean operations, they also handle the calculations of values, of numbers, right? So what we are doing now is we are moving on. Oh, by the way, since I'm here already, are there any questions about the lab, how to set up Logisim? I think a few people had questions, and I believe that once they watched the video that I prepared after the class of how to use Java in Windows, using the CLI, using the command line interface, I think that helped to clear up some of the questions. So is that correct, or do we still have any additional questions regarding how to use the command line in Windows? You could, if you want to just start it up, but using the command line interface has some other advantages. So, but yes, you can, I guess, double click on the jar file, and I think if you set it up correctly, it would use Java to open that file. There'll be a lot more, okay, command line stuff later on, and those commands will get longer and longer. So this is a good time to get comfortable with using the CLI. Well, the other thing is, I'm guessing most of you are transferring or planning to transfer to a 4-year university. I cannot say that all of them, but many of the universities rely on Linux, and also they do a lot of work on the CLI, on the command line interface. PowerShell is the trademarked Microsoft name of the command line interface in Windows, so they're really kind of the same thing. So when I use the more generic term of CLI, I'm referring to both the Bash or other types of shell in the Linux or Mac OS X environment, and also use PowerShell in Windows. So PowerShell is just Microsoft's name for CLI, for command line interface. All right, so it looks like we don't have any questions about the lab, which is due today. So we're going to move on to this module over here. It is titled Values, Numbers, and Bases. So let's go ahead and check this out, okay? And this is all about values and how values are represented, okay? So let me give you an example, okay, of what a value is and what a number is, okay, or what a representation of the value is. So value is like the price of something, okay? So let's just say that you are going to Best Buy and you want to purchase a gaming mouse, okay? I'm not really sure, what is an average price for a gaming mouse these days. So let's just say it's $36.50, okay? So $36.50 is the price, okay? That is a value, okay? So in other words, you can look at $36.50 and you can ask, well, if I work minimum wage, how many hours do I need to work to get that much money, assuming that I'm still living with my parents are feeding me, and I don't have to pay for all that stuff, right? So usually most people would kind of add up to about 3 hours, okay? So it's 3 hours worth of minimum wage to buy that gaming mouse, okay? But in terms of representation, there are many ways to represent it, okay? In other words, let's not count state tax into consideration, okay? Let's just look at $36.50. So you can bring a lot of pennies, okay? You can bring 3,650 pennies with you, go to Best Buy and say, okay, and put the big old jar or suitcase of pennies over the counter and go like, okay, this is $36.50 and I want to purchase this gaming mouse. Well, as reluctant as the clerk may be, they have to let you purchase the mouse because you do have the necessary amount of money. Okay, so that's one representation. 3,650 pennies is one representation of $36.50. Okay, I think most of you know where I'm going now. So in terms of dimes, okay, you can now bring 365 dimes, right? And that amounts to exactly the same amount of money. You can also bring along, okay, one $20 bill, one $10 bill, one $5 bill, one $1 bill, and just for kakas, you can also bring along a $half coin. Okay, so now you can present that much money, that the bills and the coins over the counter, and it adds up to the same amount. So what I'm trying to say is the price has not changed. Okay, it is still $36.50, but how you represent that amount of money has changed. Okay, depending on whether you pay everything by only pennies, only quarters, only dimes, combinations of those things, you can now change how you quote unquote represent the same amount of money. So that's basically the bottom line. Okay, that is the reason why we have values being a different concept compared to numbers. Numbers is really just a much more systematic way of representing values, but each value can be represented by an infinite number of numbers. I know that sentence sounds kind of awkward, but that's basically what it is. Okay, each value has multiple representations. So do we have any questions about just conceptually what we are talking about in this class at this point? Okay, I'm not seeing any questions. All right, excellent. So we're going to move on, and occasionally I'm going to have to check Discord and make sure it has not crashed, because sometimes it does crash, and it crashes just by being frozen. So when I look at the Discord window, it is still up, except it's not responsive. So I do have to check occasionally. All right. So what we're doing here, sections 1, 2, and 3, they're really kind of basic stuff about just the concept of what a number is and why we use certain bases. And then section 4 starts to get into something that's a little bit more systematic and a little bit more interesting. Okay, so what we're going to do, I'm going to skip a lot of the discussion, which you're supposed to have read. Okay, if you have questions about the text, you need to ask me and bring it up in class, or you can use the direct message to ask me about those paragraphs. But what I'm going to do is I'm going to skip all the way to here. Okay, so we're going to look at this number. This is all in base 10. So unless I specifically say that we are dealing with a different base, if I do not specify a different base, it is by default a base 10 number. So now I look at 16.375 and I say, well, guess what? I can rewrite this value as a sum. Okay, and the components of the sum is 10, 6, 0.3, 0.07, and 0.005. Okay. Are there any disagreement here? Are there any disagreement about the equality of 16.375 and this particular summation? Okay, very good. Okay, I wasn't expecting any disagreement or any questions, but I just want to ask. So we look at this summation and we look at each term of this summation, and then we boil each one down to, and then we say, oh, guess what 10 is? 10 is 1 times 10 to the power of 1. Guess what 6 is? 6 is 6 times 10 to the power of 0. Guess what 0.3 is? 3.3 is 3 times 10 to the power of -1, and so on. Now, you guys all know exponents already. Well, let's hope everybody is comfortable with exponents, because otherwise we have a big problem in this class. Okay, so let's just assume that everybody is comfortable with exponents. So now the question is, why do we want to look at a simple number in base 10, which is 16.375, and then we boil it down to something like this? What is interesting about this particular summation? Does anyone see a pattern? like, each term of the summation is in a particular format. They're all in a particular format. Do you guys see a pattern? And if you do see a pattern, you can just type in the text channel of what you see as the pattern. What does each term look like? There are two components to each term, and what are they? So I got a few people typing. This is good. Okay, so one component is 10 to the power of something, and then the other component is a constant. Okay, it's a coefficient. Okay, so in other words, each component of the summation has a quantity, which is a 1, in this case a 6, in this case a 3, a 7, and a 5. Okay, and it also has a magnitude. Okay, 1 is multiplied to a power of 10, in this case is 10 to the power of 1. 6 is multiplied to also a power of 10, okay, because 10 to the power of 0 is just 1, so 6 is 6 times 1, which means 6 is also 6 times 10 to the power of 0. 3 is multiplied to 10 to the power of negative 1, and there's a pattern, okay? Look at this. It's 1, 0, negative 1, negative 2, and negative 3, okay? So this is pretty systematic, okay? The way we look at numbers is actually very systematic. In other words, every quantity is multiplied by a particular power of 10, okay? And you would say, yeah, but this only makes sense, right? I mean, why would we not multiply a quantity to just a different power or different exponent of the same base? Does that sound like a kind of fair question? Well, if you have that question, or if you say, why would TAC mention anything about that? I want to remind you of the currency system in the United States, okay, which in this context doesn't make a whole lot of sense. So I'm just going to look at the denominations of common coins and bills in the United States. So the smallest one is 0.01 of a dollar, which we call a penny or a cent. Okay, the next one up is 0.05, which we call a nickel, and the next one up is 0.1, which is a dime, and then the next one up is 0.25, which is a quarter, and then we have a 1, which is a dollar. So everything after this is just multiples of a dollar. So now, what is the next one up? Well, the next one up is actually 5. Okay, $5 bills. And then we have $10 bills. So at this point, okay, everything looks kind of like, okay, I think finally we are seeing a cycle, because the next one has got to be a $25 bill. No, we do not have a $25 bill. We have a $20 bill, right? And then the next one up is then 50, and then 100, 200, 500, and so on. So there's no regularity, okay? If you look at the multiplier from one coin or bill to the next level up, there's no regularity, okay? So if you can handle a currency system like this, you already know how to do base conversion, okay? You just have not associated this concept to base conversion. So we'll get to that a little bit later. All right. Okay, so do we have any questions at this point? Both from the example of this particular base 10 number, and also from the currency denomination discussion. Okay, no questions. All right. So now we look at this particular summation and go like, hey, but this expression only works for this specific number, which is 16 times 375. So can we generalize? Okay, so you will see that this is a common theme of how I teach classes. Okay, I look for patterns. I look at ways to generalize something. Okay, so we look at this and go like, yeah, I think we can generalize, because the value being represented is really a summation of items, and each item has a multiplier, or you can call this a coefficient, and a power of 10 in this case. Okay, so that's why when we look at a multi-digit number, and the notation is d subscript I is the ith digit. So when I say ith digit, okay, there's a digit 0 to represent how many quote-unquote units we have, and then we have, in the case of base 10, the number of tens is digit 1, the number of 100s is digit 2, and so on, and then the number of 0.1s is digit -1, d subscript -1. Okay, do we have any questions? I mean, is that clear, or you guys just do not understand what I mean when I say d subscript -2? Okay, why make the subscript -1? Because we need to denote the number of 10 to the power of -1s. Okay, so doesn't hurt to give you guys an example. Okay, so we're going to use exactly the same number that we are talking about. So it's 16.375. okay, now I spaced it out for a reason. Okay, so now we look at this number and then we ask which one is D0, which one is D1, blah blah blah, and so on. Okay, why the D0 before the D1? Okay, so maybe this will make it clear. Okay, so this is D1. D1 is the digit for 10 to the power of 1. D0 is the digit or the quantity of 10 to the power of 0. And guess what this one is going to be? Can anyone give you the guess? Yep, exactly. It's D subscript -1. And obviously I did not leave enough space. And this one is D -2, this one is D -3, and so on. Okay, so is that okay? Does everybody understand now, how I determine the subscript of a particular digit? Is that okay? Now this is really important because we are going to use this notation for a while. Okay, for the next few weeks, if not more, we're going to use this particular notation. Okay, D0 is the digit representing whatever base we're going to use to the power of 0. It says D sub 0, then D sub 1. I'm not sure what you're referring to. So, all right. The formula isn't the same as the example. This is the formula. Well, okay, I see what you guys are talking about. This is 0, and then the 1, and then -1, and so on. Well, does it matter? No, seriously, that's what I'm asking. Does it matter? Isn't addition commutative? Which means you can flip the order any way you want. Nope, it is not a typo. Yep, so we have to remember addition is commutative, which means it doesn't really matter what order I list these components for adding, because I can interchange the ordering and they will still add up to the same amount. Okay, all right. But the most important part, okay, because this one here on line 3, yep, but on line 3, line 3 is not clear, okay? Line 3 only has D0, D1, and D -1, but what about D -2? Well, by implication, it's here. What about D2? Well, by implication, it's here, and so on. But it doesn't really say anything about that. And that's why we are going to use a sigma notation. So the sigma notation is like a loop, where I is a counter. And in this case, it goes from a -infinity integer to a +infinity integer, because I have no idea how many digits are actually in a number. Okay, so in that case, I'm just going to say, well, let's deal with all the digits. And a number can have an infinite number of digits. You look at this number here and go like, but Tack, This one clearly only has 5 digits. Well, I beg to differ. There's a whole bunch of zeros to the left-hand side. I just didn't bother to write them. Okay? In other words, there's a D2 over here, except the value of D2 is a 0. There's a D3 over here, except the value of D3 is also a 0. D4 is a 0, D5 is a 0. Okay? D1000 is a 0. D1001 is also a 0. Okay, so I can pad as many zeros as I want to the left-hand side, and it doesn't change the value that the number is representing. The same thing applies to padding more zeros to the right-hand side. So I can say, well, there's actually a D-4, except it is a 0. There's a D-5, except it's a 0, and so on. Okay, so instead of limiting ourselves to a certain range of number of digits, both on the left-hand side and on the right-hand side of the decimal point, I'm just saying, let's get all of them, okay? Because I just want I to be an integer, okay, which can go from as negative as I want to as positive as I want to. And the key is, what am I summing in the sigma notation? Tom just typed, and this may be backtracking a little bit, but is there a certain reason why line 3 is written that way? No. It's since it's equivalent to whether I start with D1 or not, because there's actually a D2 which is a 0, so I just didn't bother to write that, right? So there's no particular reason why I chose this particular order, because it doesn't really matter what ordering we choose to use. It is still going to sum up to exactly the same amount. All right. Are we good so far? Okay. Okay, excellent. So now the most important part is, what are we summing? Okay, each term that we are adding has 2 components. It has the D subscript I component, which means we are looking at a specific digit, and the position is I, okay? And we take that digit and we multiply that by 10 to the power of I. So if I is 0, then we take D0 and we multiply that by 10 to the power of 0, which is really just 1, right? If I is negative, let's say it's -2, okay? If D is -2, then we take the digit, which is D subscript -2, which in this case is the 7, and we multiply that by 10 to the power of -2. So the summation of each digit times the power of 10 corresponding to that digit becomes the value that the number is representing. Is that concept okay? So V is not a number. V is a value. The number is actually, what all the D's are representing. That's a number. You can look at the value as a person, okay? Whereas the digits is really just a name for that person. So are we okay with this concept when we're using base 10? Are we good? Cool. All right. So now we're going to move on and think about what can we use other bases? Are we stuck with base 10? Can we only use base 10 for numbers? Well, the answer is no. Okay, we definitely are not stuck with just using base 10. We can use base 2, for instance. Okay, so we're going to use base 2 for now as an example, and then later on we'll use some other bases. So we want to look at the same value, which is 16.375, and then we ask the question, what about this number as a base 2 number? What is going to happen when we're looking at this as a base 2 number? Okay, so what we'll do is I'm going to type up an example, so just kind of bear with me right now, because I'm going to use I'm going to use a text editor to help me type this. So let me, this is CISP310.md. All right. So what you're looking at right here is a preview of something that I'm typing, and I'm typing this off the screen, so you don't really know exactly what I'm typing. But the important part is is this. Okay, so we have a number. Okay, let's see here. We'll use a bullet point, and the number we're looking at is 16.375. So we want to express this amount, okay, in a sigma or summation of some digits times powers of 2. In other words, we are looking at, so this one is going to take quite a few more digits in base 2. So we have, okay, so we have, okay, let me switch everything into an equation form, so this way everything is kind of nice, well formatted. So let's say we have a D4, and since we're dealing with base 2, so what are we going to multiply D4 to? We're going to multiply D4 to, since we're dealing with base 2, so what is the base of our power, of our exponent? Come on, you guys can probably guess this. It's 2, right? Yep, exactly. Not 0, 2. Okay, so we are looking at this plus D3 times 2 to the power of 3 plus D2 times 2 to the power of 2 plus D1 times 2 to the power of 1 plus D0 times 2 to the power of 0 plus D, oops, forgot about the subscript here. All right, so plus, D subscript -1 to the power of -1, times 2 to the power of -1, okay, plus, let's see, we are almost there, okay, just bear with me a little bit here. So D subscript -2 times 2 to the power of -2 plus D subscript -3 times 2 to the power of -3. Okay, is that okay? Does everybody see how I'm borrowing the same value from last time, but this time because I changed the base to 2, so the digits now have to change accordingly. Okay, so the digits that we chose to use in base 10, they won't work anymore. Yes, it is indeed binary. Okay, so binary is really just a name. So, but now the question is, how do I figure out D4, D3, D2, D1, and so on? Okay, what would you suggest? Okay, in order to figure out these specific values of these. Now, let me. Google would do it. Okay, but I can. Google will do this, but it won't show you, it won't explain to you why, right? It won't explain to you why it works. All right, so I'm going to explain it, okay? That's kind of my job, isn't it? Okay, so I want you to imagine, okay, the dollar amount is $16.375, okay? So look at this as the value of something, okay? So now imagine also that the currency system, okay, the denomination of the currency system has $1 bills, okay? So you have $1 bills, you have $2 bills, you have, guess what the next one is? We're dealing with base 2, right? Nope, not 5, because we're dealing with base 2. So 4 is right, okay? And then what is the next one? Not 10, 8, and the next one is 16, 32, 64, 128, and so on, right? But these are the bills, okay? Let's look at the coins. So we have a $50, and then we have a quarter, right? Okay, that's a typo on my part. And then we have a what? What do you think is the denomination that is one step lower compared to a quarter? It is 1/8. Very good. Okay. So now, if you need to come up with this amount, okay, and in your drawer, okay, you have one of each of these, okay. So now the question is, which one do you need in order to pay for that gaming mouse that costs $16.375, okay? So how would you decide, okay? Where do you start? Do you look at the eighth of a dollar first? Where do you start? Do you start with the smallest denomination, or do you start with the largest denomination? The biggest one. Okay, very good. So can someone tell me what do I need to make up for $16 and $16.375 in this case? What do I need? We start with the largest bill that we need, which is a 16. Okay, very good. And then what do we need? After the 16, do we need an 8 after the 16 is done? No. Okay, so what would be the next one? Well, okay, Daniel is right, okay? But we kind of have to work on this step by step, okay? So we don't need after the 16, what is left? 0.375 is left, right? But the next lower denomination is an 8. So now we say, nope, we don't need an 8. What is the next one? It's a 4. Well, 0.375 doesn't have a 4 in it, okay? So we don't need a 4. The next one down is a 2. We do not need a 2 because 0.375 doesn't have a 2. Then the next one down is 1, and we say 0.375 doesn't have a 1 either. Then we get to a half, and we ask, well, does 0.375, is it at least 1/2? Nope, it is not. Then we move down to 0.25, which is a quarter, and then we ask, is 0.375 at least a quarter? And the answer is yes. Okay. So we have a quarter. So once we take care of the 16 and a quarter, then all we have left is 0.125, and the next lower down denomination is indeed 0.125. So there we go. Okay, so we just need one $16 bill, 1/4 coin, and an $8 coin in order to make up the same amount, otherwise known as $16.375. So are we doing okay so far with this conversion? Does everybody understand how to use a base to currency system now? I certainly hope the answer is yes, but I'm asking so to make sure. Okay. All right. So we look at this and go like, but it cannot be that simple, okay? Because if it were that simple, tech wouldn't use the time to talk about this. So now we look at this and ask, well, what is the other way to write this summation, okay? So we have 1 times 2 to the power of 4 plus, I'm just looking at this and trying to figure out why it is appearing in red. It could be the ampersand, it doesn't like to use the ampersand. So let me get rid of the ampersand first and see if it like that better. Yep, okay, it's the ampersand. Okay, so we got 2 to the power of 4. Where is that 2 to the power of 4 coming from? I know it's a really obvious question, but I want to ask it anyway. Exactly, the 16. So now we have another one, which is 1 times 2 to the power of, guess what it is? No, we don't have a 3. -2, yep, okay. If we follow the same order, okay, if we follow the same order on the left-hand side, the next one down is 2 to the power of -2. And then we have one more, which is 1 times 2 to the power of -3. All right. Are we doing okay so far in this process? Okay, good. But then we are still not answering the question, because the question is to figure out all of these D's, right? You know, D4, D3, D2, D1, blah, 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 blah. So it looks like we have figured out maybe a few of these D's, but not all of them, okay? So let's see what we can do at this point, okay? So now we know D4 is a 1. Does that make sense? Because we have the coefficient of 2 to the power 4 is a 1, and that's exactly what we are looking for. We're looking for the coefficient of 2 to the power 4. So is that okay? I mean, does everybody understand? Yep, exactly. Okay, but I do have to kind of spell out the entire thing. So D subscript 3 is a 0, because we do not need an 8. Okay, you know, an 8 is not needed. D to the power of 2 is also a 0, because we do not need a 4. Now I'm spelling this out for a reason, okay? You know, because even though it is pretty obvious that we have a whole bunch of zeros, I still want to spell them out, okay? Because it will help me illustrate what the number looks like in the end, what the binary number looks like, okay? Yes, indeed, okay? So a binary number, basically it's just a whole bunch of zeros and ones, because you can only have none or 1 of a power of 2 in a base 2 number, okay? So next one up is D subscript -1, and it is also a 0. We do not need a half in this case. The next one down is D subscript -2. We do need one of those. And then the next one down is D subscript -3, and we also need one of those. Is that okay? I'm just really spelling out every single digit of this base 2 representation. And Tom has a question. How does it know we are talking about decimal? Okay, well, at this point, I don't need to specify anything in base 2. You can look at these as decimal as well as base 2, because the 1 is representing 1 no matter what base you're using. Does that make sense? 1 means 1 in base 2, 1 means 1 in base 10, 1 means 1 in base 16, and so on. And then 0 is the same way. So 0 and 1 are common digits that are shared by just about any base, because the smallest sensible base is base 2. And we have a whole bunch of people typing, okay? So 10 in base x is x. Not quite sure. Yes, okay, I see what you mean. So 1 0, okay, not 10, but 1 0 in whatever base is the base itself. That is correct. Because, okay, so let me restate that in my whiteboard here. Okay, so let me specify that. Okay, so the way we specify a base is simply to use parentheses right after the number, or subscript. So subscript is much harder for you guys if you're using a text editor. So I'm just going to use parentheses to indicate the base. So I'm going to use B here to indicate whatever base we're using. Okay, so B can be 2 for binary, it can be 10 for base 10 or decimal, it can be 16 for hexadecimal, and so on. Okay, so the value of this number in base B really is just B to the power of 1. Okay, so and that's basically the essence, okay, of base conversion is whatever the digit, the position of the digit is indicating the power of the base. Okay, let me reformulate my sentence. The position of the digit dictates, whose coefficient it is, and in this case, the who is the power of the base raised to the position of the digit. Whew. Okay, I'm not sure whether that turns out to make sense to you guys or not. Okay, how would we account for numbers that aren't direct powers of 2, such as that? Well, you approximate, okay? It's just like, 1/3. How do you spell out 1/3 as a decimal number? It's not 0.3, it is not 0.33, it is not 0.333, it is not 0.3333, and so on, because in base 10, it will take an infinite number of digits on the right-hand side of the decimal point to represent the value of 1 divided by 3. So 16.377 is going to be like that as a base 2 number. You cannot just use a fixed number of digits to the right-hand side of the decimal point to represent 16.377. It's going to be there will be some recurring pattern, after the decimal point. So that's a very good question. But it's going to be, you cannot use a fixed number of digits in base 2 to represent 16.377. I just chose 16.375 because it's nice and clean as an example. All right, so getting back to what I was actually planning to show you guys, okay? So now we look at all these digits and go like, well, we can now spell out what is D4, what is D3, what is D2, what is D1, and so on. Can we look at the binary number that is representing 16.375 just as a number, okay? Well, that's actually super duper easy, because all we now have to do is to string all those digits along, and then we just say, oh, when you look at the entire thing, it is really just 1 followed by 4 zeros, 1, 2, 3, 4, and then a point, and then 0, 1, 1, and it's base 2, so I'm gonna use subscript 2, but it is the same thing as in parentheses 2. All that is going to say is to emphasize that this is not a base 10 number. This is not 10,000.011. It is 0.011 in base 2. So are we good so far? Are we understanding how to the concept of base conversion, or what numbers actually do, or how a number is used to represent a value, or that a value can be represented by different bases if you want to. Okay, cool. All right, so let's do some exercises. Okay, so we're gonna do some exercise and try to use some really oddball bases. Okay, because base 10, we are used to it, even though it kind of sucks as a base, because anything that's not really a power of 2 kind of is not very friendly on a computer. Okay, base 0.5, let's see, that would be a problem, wouldn't it? Because 0.5 to the power of anything. Okay, the largest power of 0.5 is 0.5 to the power of 0. So if you try to use a base 0.5, you cannot represent anything that is at least 1. So even 1 cannot be represented. Well, I take it back. 0.5 to the power of 0 is 1 indeed, but you cannot represent anything that is at least 2. Oh yeah, you can just flip it on the other way. Yeah, I see. Okay, so base 0.5 is the flip side of 0.2. I get it. That is pretty smart. Okay. Does everybody see, how, you can have a base 0.5, because the negative power are now the ones that have a larger value. They are basically coefficient. They become larger in terms of value. Yep, so Aiden is correct. Pretty smart. Cool. Okay. But we'll do something that is a little bit less confusing, but nonetheless probably a little bit confusing to some people, okay? So we'll go ahead and do this anyway, okay? Because I like confusing stuff. I get fascinated by confusing stuff. So we'll look at 671 as a base 10 number, and then we look at this and go like, what does it look like as a base 7 number? Okay, so how do we do this? How do we figure out what 671 as a base 10 number, as a base 7 number, what is that going to look like? Okay. Yes, I know some of you are going to say, let's Google it. Well, what if the internet is down? Okay, what if you cannot Google? Then what are you going to do? Okay, so this is what we're going to do. We'll first explain the concept. Okay, so we have 671. Okay, yes, we want to figure out the coefficient of powers of 7. So in this case, we have, let's see, do we need a D2? I don't think we do need a D2 in this case. So we have a D subscript 2 times 7 to the power of 2 plus D subscript 1 times 7 to the power of 1. It will look nice once I finish this entire thing, plus D subscript 0 times 7 to the power of 0. Okay, so now what we are trying to do is to figure out what D2, D1, and D0 should be. Okay, so which end should I start with first? Should I start with the number of D to the power of 2, which are the 49s? I think we need actually one more, don't we? Because 6 times 49 is not quite enough to cover everything that we need. All right, so we need a D3. So we have a D3 times 7 to the power of 3. There we go. So now we are. That is fast. Okay, but how do we know what D3 should look like? What do you guys think? Okay, if I just want to single out D3, okay, how do I calculate D3? Well, no, I'm not going to give you the final answer because the final answer is actually in the notes itself. But I want to guide you through the thinking process. Okay, how do we know what D3 should look like? Okay, so what we'll also do is we're going to look at the value as V. So this way I can just refer to V instead of 671 to make it slightly more general. All right, so we know that we are looking for the number of 7 to the power of 3s, right? So it kind of makes sense that we want to look at V divided by 7 to the power of 3. Does that make sense? If you get a return of a remainder, okay, we'll deal with that later. Okay, so we're doing a rough draft at this point. So D3 is approximately V divided by 7 to the power of 3. Would everybody kind of agree that this is a starting point? It's not going to give you exactly the answer, but it's a starting point. Does that make sense? Okay. So now we look at this and go like, but Tech, this is not going to be a even number. Okay, if you use a calculator and figure out what is 671 divided by what 49 times 7, I don't even know what that is. Okay, I'm gonna cheat and use a calculator or a spreadsheet, better yet, to do this. Okay, and guess what? In our exams, you can use calculators, spreadsheet, and the internet too, as long as there's no live collaboration. Okay, so we are looking at 671 divided by 7 to the power of 3. Uh-oh, did I mistype something? Yep. There we go. So it's 1.95 blah 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 blah. Okay, well, if it's 1.9 something, then what do you think is actually D3? Because it's a single digit, it cannot be 1 point something. So you only got two sensible choices, right? It's either 1 or 2. Which one do you think it is? It's a 1. Okay, so that means we are not rounding, we are taking the floor of this thing here. Okay, so now we have to add something to this. So we now say it is the floor, and let's see if this works, okay? Because I think it might work. There we go. So this is the floor symbol. to take the floor of a value is to find the largest integer that is less than or equal to the value. Okay, I'm going to spell out down here. Okay, the floor of some value x is the largest integer that is less than or equal to the value of x. Okay, so well, that seems to work fine. Okay, because it seems to work. Except I want an equation that works even better. Okay, I want something that works for all of the other digits. So let me just add something to this, and you guys can tell me whether it will mess up the calculation or not. What if I were to add a mod 7 right here? Okay, oh, I forgot to put it inside the $sign, so it doesn't look, now it looks right. So would that still work? I mean, would it mess up the calculation? No, it does not mess up the calculation, right? Because the digit itself, okay, if I'm talking about a number in base 7, each digit can only go from 0 to what? I want you guys to kind of think about this and answer this question, okay? Exactly, okay, Tom is so quick. Yes, so in base 7, each digit can only go from 0 to 6. So that means modding what I think is the answer already by 7, it's not going to do a single thing, okay? It's not going to mess it up. But what mod 7 is helping me to do is now I can use the same equation to figure out what is D2. Okay, so let's try to figure out what is D2. So D2, okay. So if I don't use this method, then I have to think about, okay, let's take 1 times 7 to the power of 3 out of 671 first. Then we can try to figure out what is D2 using that equation. Well, that's a lot of steps, okay? So instead of doing that, I'm just going to say this is going to be the floor of dividing v by 7 to the power of 2, and then we mod it with 7. Okay, so I don't even bother to remove certain values from v before I move on to the digits of the lesser powers of 7. And the mod 7 is what is doing this trick. Okay, so let's just carry out this calculation and see how it works. Okay, so we'll go ahead and carry out this particular calculation. So we are looking at 671 divided by 49. Okay, and using my calculator over here, we can now say, my cursor is at the wrong place. There we go. 671 divided by 49 is 13. Okay. This is 13 point something, blah, blah, blah. Okay, so we'll just put a bunch of question marks here. So obviously 13 cannot be a digit of base 7. So what do we do with the 13? Well, we have to mod it with 7. Okay, so D2 is actually 13 mod 7, and that turns out to be what? 6, right? Are we good so far? Oh, Tom had it right in the Discord channel, but he just explained that he was trying to type 7, but instead he typed 6. The answer is 6. Okay, that is actually pretty funny. But in whatever base you're using, you can only express 0 to the base minus 1 as a single digit. And then some people go like, wait, that doesn't make sense. That is not the case in base 10. Then I would challenge you to use one single digit to represent a quantity of 10. You cannot. right? Because we only have digits from 0 to 9. The quantity 10 requires, guess what? 2 digits. It requires a 1 and a 0. That 1 is representing that we have 1 of 10, which is our base, to the power of 1. And that's why the 1 is the D1 when we look at 10 in base 10. I know that doesn't sound very good, but that's kind of what we are explaining. All right, so remember a little bit earlier, I like to look at patterns so that I can figure out a generalization of how to do something in general. So this is something that we can observe. It's like, oh, so based on this observation, I just erased something, one too many things. So if we want to do a generalization, so it looks like, okay, the ith digit that we are dealing with is generally the floor of V divided by, in this case, because we're dealing with base 7, so it is divided by 7 to the power of whatever I is, okay? And after we take the floor of that division, we have to remember to mod it with 7. Does that make sense? Is this looking like a reasonable generalization of what we have just figured out? Perhaps, okay. Well, I mean, if you look at it, I mean, D3 is V divided by 7 to the power of 3 mod 7. D2 is V divided by 7 to the power of 2 mod 7. So it kind of looks like, we have a generalization, right? But this generalization is not as general as we want it to be, because this only works in base 7. Right? Because we have this hard-coded constant of 7 here and also here. So if you want to generalize and say, I want a super generalized equation for any base, okay, and the base is represented by B, what do you think that equation is going to look like? We take all the 7s out and replace all the 7s with B, because B is the base. B, that's right, Daniel, B, not D. All right, so I'm just going to be a little bit lazy, do a little bit of copy and pasting, and then we abstract it, okay, we generalize. So B is representing the base, and B is representing the base, and B is representing the base. Woohoo! So now we got a very general equation that will help us figure out a single digit, okay, when we want to represent a value V in a particular base. Is that okay? Okay, I got a question, okay, so I got a question of, what if this I is negative, is a negative integer? Would this still work? What do you think? Do you guys want to plug this equation in using the example that we got earlier? Yeah, I hope so. Come on, say yes. Okay, very good. All right, so the way we're going to do this is a spreadsheet. There's no way I'm going to do this by hand. Okay, that is just way too tedious. So we're looking at the value of 16.375. Okay, that's just in base 10. Nothing fancy about this. And then we'll look at the base. Okay, so let me be just a little bit nicer here so that we can actually see what we're dealing with. This is V, and this is our base. We'll start with base 2 first, okay? Because we just did it before, but we want to be able to get back to exactly the same number using this generalized equation or formula. So now we can now look at the I, okay? So I can go from a certain number of negative value to a certain number of positive value. So let me see, what do I want to do here? Okay, we'll start with some negative value and then work ourselves to positive values. Okay, so let's just say that we'll start with -10, and then each number is the one previous plus 1. Okay, so this way I don't need to type -9 by hand. Okay, as you can see, if there's an easier way to do something, or more systematic way to do something, I usually will try to find it and do it that way. Okay, so now we want to compute di. Okay, all right, so this is where we plug that equation in. So as I remember the equation, first of all, we have to take the floor of the value divided by the base raised to the power of the position, which is I, and then we want to do a mod. Okay, so this is why it's a little bit awkward, because in a spreadsheet, mod is a function and not an operator, so you kind of have to wrap the value that we already have inside a mod, and we want to mod it with the base itself, like so. Okay, but this is not ready to be duplicated, because if I were to duplicate this, then the row number would actually change depending on which row we are dealing with, and certain things of this equation really should not change the row number. So any references to B1 should continue to refer to B1. So we put a dollar here so that when we replicate this equation or this formula, B1 will always refer to B1. It won't shift along with other things. And B2 is the same way. And only A5 can float. Okay, so so-called float. So when we combine all of this stuff here, this is the number that we should see when we convert 16.375 to a base 2 number. So now the question is, where is that point? Where is the decimal point? The decimal point is basically a mark that is between digit 0 and digit -1. So if I were to draw a line to represent the dot, I would draw a line on top of these cells. So let me do that. There we go. All right. So this bar is representing the point. And the more significant digits are on this side, the less significant digits are on this side. All right. Yeah, well, and it's free too, Daniel. I'm not charging anything extra. The district is not charging anything extra to learn how to use a spreadsheet. Isn't that cool? Most cost-effective, perhaps. All right, so now we want to potentially make this look even nicer. So let me see if I can do concatenation in Libreoffice. I know I can do this in Google Sheet, but Libreoffice is a little bit different. So I'm just going to look this up on the side. And it has a concat function, but I want something that can concat multiple strings, and looks like we can indeed do all that. Cool. Okay, so this is what we can this is what we can do to look at the entire thing. So we are looking at 2 concats. And oh, we need to flip the order. That is going to be a pain. Okay, I don't want to do that, because I don't think I can do cell reference in reverse. I can give it a try. So B25 down to B15. Okay, so let's see if that works. No, it doesn't work. The ordering is opposite. I suppose I can try to find a function to reverse the order. So let me do that. Sorry about the digression here. I'm consulting Google as we speak, by the way. There's no quick and easy way to do it. Darn it. Okay. The solutions that I'm finding are kind of not something that I want to do. Okay. Okay, let me see what Daniel or Anna. Okay. We can sort column A. No. I suppose I can change the order, instead of using increasing order, I can use a decreasing order, then everything would actually look right. But I'm not going to do that, okay? Because that's not the main point of what we are doing here. So when you read the number, we have to read from here to here, okay? So if you, okay, let me just put it this way. If you were to tilt your head counterclockwise by 90 degrees, then you would actually see the number, okay? So if you were to counterclockwise tilt your head, then you will see that the number is 10000.011, which is exactly the same number, binary number that we got, okay? So we are not surprised, right? Because, well, this is kind of what we got last time. Let's change the 2 to, as Aidan suggested, 0.5. Okay, so Aidan gave us a great idea of changing the base to 0.5. So remember this picture before I press the enter key. Okay, bam, and it does not work. Why is it not working? Doesn't make sense. Oh, okay, the equation doesn't make sense, doesn't work because, okay, I have to rework that equation so that it can work with a different base. Okay. We can change it to other bases too. Base 4 would actually work nicely. Okay, so before I press the enter key, let's do it by hand first. Okay, so I'm going to do the escape here. So in base 4, what do you think 16.375 is going to look like? So we have, let's list out all the powers in base 4. Okay, so we have 4 times 4, which is a 16. 4 is just 4. 4 to the power of 0 is 1. And then we have a quarter, and then we have a 16th, and so on. Okay, excuse me, the 16th doesn't look right, so we'll do it one more time. Oh, it doesn't like it. It thinks it's a date, okay, and once it thinks it's a date, it doesn't want to revert back to something else. Okay, so we'll change that. What is the format? We want number, and we just want a number. There we go. It's 0.0625, by the way. Okay, so now we want to look at this number and go like, how many 16 do we have in 16.375? I'm pretty sure that's a pretty obvious answer, right? It's a 1. Once we take care of the 16, there are no 4s and no 1s that we need. What is left is 0.375, so it does have a quarter, but once we take care of the quarter, we have 0.125 left, which means we need 2 of the 16th in order to make up the same quantity. So in base 16, this quantity would look like 100.12. Is that making any sense? Are we okay so far? Good? Okay. So now I just go here, change the 0.5 to a 4, and see if we get the number back. Remember, you have to kind of rotate your head by 90 degrees counterclockwise. So we have 100.12, and that agrees with what we have here. Cool. Do you guys want to try this with a really awkward base like 7? Why not? So if you want to look at the quantity of 16.375 as a base 7 number, then it will read as 2. It makes sense, right? 2 times 7 is 14 with a remainder of 2, so it's 2 point, and then it's infinite recurring pattern of 2 after that. So 22.24242424 and so on is representing 16, what we know as 16.375 in base 10, except this will work when you're using base 7. So this spreadsheet works out for any non-fractional base. So any base that's at least 2, it will work. And Daniel is typing something. He's cooking something up. So let's find out what Daniel has just cooked up. I'm not sure. Okay, so accuracy has to do with how many digits we give the number, how many digits we are allowed to use. So there's no inherent accuracy difference between the bases. In other words, a number in base 16, is not any more accurate compared to a number in base 2. It's just that in base 2, you will need more digits to express the same accuracy. Precision, given the same number of digits, yes. But if we are not talking about a fixed number of digits, then there's no actual comparison, because any number in any base can be just as precise. Is that okay? So now is a good time, okay? We still got about 8 minutes to go, but it's a good time to tell you guys what today's keyword is for the role-taking activity. Since we have been talking about base 7, so the keyword is, okay, let me put it in my virtual whiteboard here, okay? Today's role-taking password is heptapod. And you guys would go like, heptapod, is that really even a word? What do you think? If you look up heptapod in Google, what do you think is pretty much the first thing that pops up? And I know exactly. Did you just Google it, Tom? Or did you? Okay. Yes, so there's a movie called Arrival. Great sci-fi movie. And in that movie, the aliens are heptapods. They have 7 limbs instead of 8. It's actually a very, very interesting movie. It has to do with kind of language and not time travel, but being able to see the past and the future at the same time. So it's kind of a very interesting movie. I will let you guys watch it to figure out what it is. Okay, but if you are a heptapod, okay, then it only makes sense that the number system that you'll be using is going to be base 7. We use base 10 only because guess what? We got 10 fingers. Is that okay? Are we good? Now, the next question, okay? So I want to complete today's lecture by bringing everything to a full circle, okay? If we look at this number, okay, this is 22.242424, how do we reverse it back to the value of 16.375, okay? In other words, if this is hidden, okay, if this is not given to you, let me see how I can hide that. That works. Oh, it just inverts it, okay? It's not, okay. There's no quick way to hide it. Okay. How about gray, like gray in the middle? No, it doesn't do that either. So I can do something that's close to black, but not quite all the way, so it doesn't invert it. Oh, this is frustrating. I just want to change the background color so it looks like the foreground color and it won't let me do it. It's a little bit too smart for that. Okay, so if I do not know what the value is, I'm only given a number in a particular base and all the digits. How do I figure out? Can you scroll down one? Oh, you mean moving this up? Okay. Like scroll the bar on the right down one cell. Scroll the bar on the right down one cell. Oh, okay, I see. Just scroll it so that you guys cannot see it. Okay, I get it. Okay, so how do we recalculate? Okay, so the idea is not knowing what this number is, but given the base, okay, this is our base, given all the digits, okay, a fixed number of digits in that base, how do we figure out what value is represented by the number? Okay, so to reverse the whole process, you just have to say, okay, this is, whatever the base is to the power of 10, and we got 0 of those. So the value contributed by row 25 is going to be the base, which is this number here, raised to the power of this number here, times the coefficient, which is this one over here. Now we have to put a $sign, next to the 2, because otherwise, I cannot copy and paste the cell because that number will start to float. So it's a 0. And now that we know the formula of this, we can now just kind of drag it. So now what we're getting is each number. Okay, let me pick something that's non-zero. Let's pick this one here. Okay. So this number, which is 0.001665973, blah 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 blah. There's a whole lot more to it, but what it is really representing is what digit -4 is representing when the value of that digit is a 4. Okay, this is the quantity contributed by D -4 when D -4 is 4 in base 7. Okay, so when we want to look at the value of the entire number, we just have to add up everything. So if we are to take a summation of what each digit is contributing, then we should get something that's really close back to whatever we start off to begin with. Is that okay? Because I want to show you how to get to a number in a particular base, but I also want to show you how to reverse the process. If you are given a number in a particular base, how do you find out what value the number is representing? It's actually really just that. So are we doing okay, with today's lecture? All right. We got 1 minute to go, and you guys have a new lab. So I got to talk about the new lab just a little bit because you need a key to participate in the new lab. So how would it go directly from base from a base like 7 to something other than base 10? You need basically 2 spreadsheets. One spreadsheet to generate a number. Well, we look at this number. We look at this value as a base 10 value only because spreadsheets are designed for human beings, and it makes the bold assumption that all human beings prefer base 10, right? So if you have 2 spreadsheets like this, and then you can basically just use the value like this one, and copy this to this cell of the next spreadsheet, then you can change the base to whatever you want. You can interchange between any base you want in that case. Okay. All right, so one more thing before I end today's lecture so that you guys can move on to the lab or start your weekend early, which is not what I would recommend, but I know some of you want to do that. So I want to let you know today's labs. Okay, the passcode of today's lab is not heptapod. It is octopus. No, I take it back. It's Nandroid. Okay, because we're still dealing with the NAND gate with today's lab, so we are not quite doing the base conversion lab yet. Okay, so this way, it gives you guys a whole weekend to review the base conversion stuff before we have a lab on base conversion. So today's lab is only about the NAND gate, so I name it. I chose the passcode of Nandroid. All right, so we are pretty much done with today's lecture, but I'm waiting for for people to finish typing, just in case it is relating to the whole class. Then I can go ahead and talk about it when we still have everything being recorded. Okay. No questions? All right. So if there are no questions, just remember these two things. The role-taking password is heptapod, and then the passcode of today's lab. Let me show you which one we are talking about. So today's lab is the NAN2 lab, which depends on what you did on Tuesday. So I hope you guys kept your file on Tuesday. Well, otherwise you can just kind of reconstruct it. The second time you reconstruct it, it won't take nearly as much time. This one is due on September 1st, which is next Tuesday, right before the synchronous lecture. So you got about 5 days to work on this one. Okay, that's a lot of time to work on it. All right, so I'm going to ask one more time, do we have any additional questions before I stop the live stream? No questions. You guys cannot wait to get on to your long weekend, which is why I do not like Tuesday, Thursday classes. The weekend is way too long. All right, well, I will be next to my computer, to answer questions about the lab NAN2 or anything related to the lectures, until 9:50 p.m. Okay, so even if you guys are to take a long weekend now, I'm not going to start one until I'm done with this class. I'm staying on this class until I'm done. Well, it is on Canvas. Tom, it's right here. I mean, you won't see as many items, but it's on Canvas. It's right below the Logicium Setup Lab. You should see it now. Yep. So it's kind of like the previous lab, where it has its own instructions, to kind of guide you through step by step. And I'll be here until 9:50 to answer questions. So if you guys are to start on this one now, I think most people can get it done before 9:50. Then you have a more relaxing long weekend instead of a weekend where you have to kind of remember, oh, I still got that lab to do before Tuesday. Yep. Okay, cool. So I am going to drop out of, I'm going to stop the live stream, and then I'll stay on the text channel. But I'll give myself 10 minutes to eat something first, and I'll come back and answer questions. Have a nice weekend.